start recording this. So Z is 7th, using your foiling process that you know from Algebra 1, Algebra 2, the work you've done with complex numbers in Algebra 2, gets you down to this. And that took us, I think the last class, I didn't time it here, but the last class that took us like 7.5 minutes to do. Okay? Let's do it a different way, and let's see if we can reproduce the same answer. So I'm going to write that answer up here real quick. Actually, do that. All right. Now, there is some preliminary work that we have to do here to be able to use de Moivre's theorem, but my hopes are that you find out that this is much quicker. Okay. So we're going to find 2 root 3 plus 2i to the 7th power. First thing I do is put this thing in polar form. Because remember, this is rectangular, so we're going to go polar. Okay. So remember, polar form is equal to r cis theta. So we need to find those two things, r and theta. So r is a squared plus b squared under the square root. So if I take this square that, I get what, 4? And square that, I get 3, so that's 12. All right, and then I square this, so I get 4. So that gives me 4 to be r. Does that make sense? Okay. Theta then, the only thing you got to pay attention to when you're finding theta, because your calculator obviously isn't going to give you this right back in maybe the format that we need, but when it goes 2 radical 3 plus 2i, know that that is in the first quadrant. So you can know, is the value that I get back on my calculator exactly what I need, or do I need to adjust that based on the quadrant that z is in? All right, so I should be able to take theta is equal to tangent inverse of b over a. So 2 over 2 root 3, which that's just root 3, so it goes tangent inverse. This becomes 1 over root 3, which is root 3 over 3. Hopefully by now we know that that is how many degrees? Does anybody know? Good, it's 30 degrees, or I heard somebody say pi over 6. So pi over 6 is what we're looking at here. So we now have r and we have theta. So let's put this thing in polar form. So z would look like 4 cis pi over 6. Okay. Now, de Moivre's theorem says if you're going to take z to the nth, then you take your r, you raise it to the nth, and you take your theta, and you multiply it by n. All right, we're going to the 7th power, right? So our n, so z to the 7th would look like 4 cis pi over 6 raised to the 7th. I'm going to rewrite that then as 4 to the 7th. Cis of, I take my theta of pi over 6 times 7, so 7 pi over 6, right? Well, 4 to the 7th is 16384. And then I have cosine of 7 pi over 6 plus then 16384 I sine of 7 pi over 6. So I expand that. You don't have to expand that if you know what cis means. You got to keep things straight in your head. I think, though, if you're trying to eventually evaluate this so we can get into that form right there. What is the cosine at 7 pi over 6? Yep. Negative radical 3 over 2. What's the sine at 7 pi over 6? Negative 1/2. If I take this number 16,384 and I divide it by 2, becomes 8192. And then becomes minus 8192 I. Is that then the exact same thing we found there in red? Okay. And that took us only a little over 3 minutes. Okay. So 7.5 minutes compared to 3 minutes in terms of efficiency. rather do it this way, right? And now you can start to see, okay, maybe you're okay giving up 4 minutes and doing this long one. All right. What if I made that 7 a 17? Or maybe I made that 7 a 70. Okay. Do you want to do that the long way? No. Okay. There may be, a lot of our like computer programs and stuff like that. If they're using complex numbers for some reason, they're probably going to do a lot of the work and the math in polar form because it's more efficient. It's less coding. It's less memory and RAM and stuff like that, which means it's cheaper to make. Okay, cheaper to operate, cheaper to buy, that kind of stuff. I think the number one place that you guys would see complex numbers kind of being applied the most is through electricity. Okay, and I don't know a whole lot about it other than it hurts when you shock yourself, but there are things in electrical circuits like resistance and ohms that are attached to that that we like to have two quantities representing. Okay, and complex numbers allow for that. Okay, so it's very, very beneficial, which is kind of neat because complex numbers obviously were developed way before we could harness electricity. All right, but then we find out that they have an application in that technology. Okay, which I think is cool about mathematics in general, is that a lot of the stuff that we use currently in our technology was developed, hundreds of years ago. Okay, this De Moivre he was alive in I think 1677 or something like that. Okay, prime numbers, for example, prime numbers. We've been interested in prime numbers since 300 BC, stuff like that. I mean, people were working on it for a very, very, very long time. Okay. Turns out prime numbers have a very, very, very useful application in encryption. Okay. If you guys know anything about computers and passwords and stuff like that, bank accounts and encryption, prime numbers allow for that. Okay. Something that the creator or the people that were interested in very large prime numbers didn't really understand or knew it was going to be used for. But without prime numbers, we don't have encryption in your bank account's not secure without them. Does that make sense? Okay. So I just think that just a kind of a side note for all of mathematics is kind of an interesting thing. So when you guys are doing it, that's a handful of examples. We did 2 yesterday, did 1 today. There's a couple examples in like the first period video, so please watch those as you're working through your homework. You're gonna need to be able to do that process, but they're all very similar. Okay, so I think at this point, maybe seeing just a couple examples, we have the skills to kind of work through those. I want to work on finding some complex roots today. I want to find the nth roots of complex numbers. So I'm just going to write of a plus bi. Okay, the nth roots of a plus bi. I'm just going to write out here kind of the theorem that this thing is explained. It says if z is equal to r cis theta, and n is a positive integer, then z has the n distinct nth roots that look like this. Okay, so this is how we're going to represent an nth root. We use just I'm not sure if it's a w or if they're trying to use omega here. I just call it w. W sub k is equal to r to the 1/nth cis of theta plus 2 pi k over n. And then we say for k starting at 0, 1, 2, and all the way up to n minus 1. Okay, so if I'm trying to get it now, try to take the nth root of something. Taking the nth root is the same thing as raising to the 1/nth power, isn't it? I'll take the square root of something, that's the same thing as taking to the 1/2 power, raising to 1/2 power. I'll take the cube root, it's raising to the 1/3 power. So when I see that r to the 1 over n, that's talking about taking the nth root, okay? So here's kind of what this is going to look like. Let's say we have, get an example here. Try to do one differently than what we did yet or in the last class. Let's say, all right, we're going to take the cube roots. So what this means is that there should be three complex numbers that I can multiply by themselves 3 times to get 4 root 3 plus 4i. Okay, so that is your z. Okay, and when it says find the 3 cube roots, what we're interested in, what that's basically saying, it says find z raised to the 1/3 power. And there should be 3 of those results. Okay? And I think recognizing the 3 results and the reason or the purpose of having 3 results or why they exist makes a little bit more sense after we get the answers, and I can show you what those answers mean and what we can do with them. So let's just kind of work through this process. So z is equal to 4 root 3 plus 4i. We are trying to find z, the cube root of z. In order to do this, this is part of de Moivre's theorem, and it's in polar form, right? So we got to change this thing to polar form, okay? So r is going to be 4 squared, so that's 16, right? Times 3 is 48, and then plus this 16, so it's 48 plus 16. 64, isn't it? So r ends up being 8. Now I got to find theta, which is going to be tangent inverse of b over a. So 4 over 4 root 3. Again, that becomes tangent inverse of 1 over root 3, which is root 3 over 3. And we've already done that one. That's how many degrees? 30 degrees. Or pi over 6 radians. The only thing to be careful here, guys, is make sure you know what quadrant that is, just like always. That's in the first quadrant, right? So in my calculator, if I use tangent inverse of radical 3 over 3 in my calculator, it spits back 30. I know that 30 is what I use. If it was in the second quadrant, I probably wouldn't use 30. Does that make sense? Okay. For instance, if I was on my calculator, let's say this was 4 root 3 minus 4i. So 4 root 3 minus 4i would be right there. Actually, let's make it negative 4 root 3 plus 4i. So if this was a negative right here, that would put that point over here in that quadrant, correct? My calculator is going to spit back negative 30 to me, though, as an answer. So what we need to realize is that 30 that it spits back is that angle, and I'd really use 150 instead. Does that kind of make sense? So you just got to be cautious of that. In this case, because 4 plus 4i, or 4 root 3 plus 4i is in the first quadrant, it's not a big issue, but it does happen quite a bit. All right, so now we know that z in polar form looks like this. Z looks like 8 cis pi over 6. Okay? So if I'm going to find z cubed, or sorry, cube root of z, or z to the 1/3, would that look like this? 8 cis of pi over 6 raised to the 1/3. Does that make sense? Now we apply this rule right here. Okay, I'm just going to write this as kind of an arbitrary w sub k. So write a formula that's going to help me generate all of these different roots. And all you do is you take your r and you raise it to that power. So I get 8 to the 1/3. And then I'll have cis. And now I take my theta, which is pi over 6. I'm going to add 2 pi k to that. And I'll divide that by n. What is n in this case? It's 3. Okay? So that right there is your... I'm going to say it's kind of your formula. It's going to generate your 3 roots because it's in terms of k, right? So then this says for k equals 0, 1, 2, all the way up to n minus 1. So if k, let's kind of do the work up here. If k is equal to 0, this thing becomes 8 raised to the 1. But now what's the cube root of 8? Let's just kind of simplify that. What's that going to give me? 2. Okay, so when k is 0, it provides me 2. Cis, now if k is 0, this goes away, right? 2 pi k goes away. And I just have pi over 6 divided by 3, which is pi over 18. Okay? That's one of my cube roots. If we need to change that to rectangular, we can kind of at the end here. If k is 1, it's 2 cis. Now I'm going to have pi over 6 plus 2 pi. Okay, so that's what, 13 pi over 6 divided by 3, so that becomes 13 pi over 18. Is that okay? And I'll give you a shortcut here in a moment to find these other k's. But k being 2, I'll come down here, plug in 2 for that k, gives me 4 pi, which is what, 24 pi over 6? So 24 pi over 6 plus pi over 6 gives me 25. Pi over 6 divided by 3 makes that denominator 18. And now here's kind of the short, because I don't want to have to do that. That's a pain in the butt every single time k increases, isn't it? What do you recognize that the common difference between my thetas is right there? 12 pi over 18. Is that same there? Yeah. So if I need to go another one, I would just add 12 pi over 18 to that previous one. Does that make sense? So you can do that. That's fine. It works. Again, if you need to change these into rectangular, you could do that. Now, do you know off the unit circle what pi over 18 is? Is a nice nice fraction with radicals in it and stuff like that? No, that's not common. If this was like pi over 6, pi over 3, pi over 4, and those multiples, you could by all means change this to rectangular real nice. I'm going to take GeoGebra and allow GeoGebra to do this for us. Desmos does not do this. Desmos doesn't know what I is, at least in regards to, as much as I've messed around with it, I can't figure out what it, whether it has that capability or not. So again, Desmos fails us. All right. So what I want to do first, guys, is I'm going to plot the point that we started with. The point that we started with was 4 times the square root of 3 plus 4i, right? Plus 4i. So that is, where's that? That's that point right there, okay? Now, when I take the cube root of that, okay, one of those cube roots is this 2. Now, when I do polar form on GeoGebra, I have to type in cosine of pi over 18 plus then I sine of pi over 18. It doesn't know what I mean when I say cis, okay? Or type in cis. So that's going to be, let's just call that, let's go W sub 1 is equal to that, okay? So that is that point right there. Is that okay with everybody? And you see GeoGebra went ahead and actually converted it into rectangular coordinates for me. I'm going to cut and paste this so that I can get the other roots a little bit quicker. So that it becomes 13 pi. All right, and that's W sub 2. Okay, and then I'm going to do it one more time to find W sub 3. And I don't care, guys. You call it Z sub 3, Z sub whatever you want to. If you want to use W's, that's fine too. It doesn't matter. So 25 should be that multiple. So we'll do that. And those three things then, those 3 points are your cube roots of that one. Now why? Well, what a cube root means is that I should be able to take that number and multiply it by itself how many times to get that number? 3 times. So let's see if I can take W sub 1 and multiply it by itself 3 times. So that'd be cubing it, right? Does that give me the same point right here of Z sub 1? Apply it on top of it, right? If I take W sub 2 and do the same thing, it plots right on top again. Okay, so you're seeing all these plotting on top. And if I do, again, W sub 3, raise that to the 3rd power, it's right there. Does that kind of make sense? Those are the only 3 points in the complex plane that when I cube them, I get this point right here. Okay. Now, let me ask you this. Are these relatable to one another? Absolutely. They should be relatable to one another. If I take what was our radius for this circle? Think about when we did the radius here, the radius was 8, right? So if I do x squared plus y squared equals 8 to the 1/3. What's going on there? Oh. Hold on a second. Let's get this way. My radius was 2, right? 8 to the 1/3. My radius was 2. So when I square that, I should get 4 in my formula. I'll put 8 in there. Hold on. But I guess I put 2 in there instead of 4. All of those points are on that circle, right? Any guesses on how many degrees are between W1 and W2? $120 degrees, right? Okay. Why? Well, 360 divided by 3 is 120, right? And that's what we were doing. Now, we were using pi, but we're doing this right here. 2 pi divided by n being 3, we have 2 pi over 3 right there. Okay, so that's that multiple of 120 that's occurring there. So there is always kind of a symmetry related to being expressed when we start finding these roots. Okay, if I were to take the same point, so that point, 4 root 3 plus 4i, you can find the square root of it, you can find the cube root, you can find the 4th root, the 5th root, and as I start finding more and more roots, obviously start getting more and more kind of compacted together on that circle. Does that make sense? Okay. Let's do one more. And it's kind of, and this is, it's actually intended, and we did the exact same one in the last class. All right, let's do this. They did the eighth roots of 1. So last class did basically if z was equal to 1 plus 0i, or just 1, we wanted to find the 8th roots of z. Okay, so we did that. So let's do something different but very similar. Let's say that we're going to find z is equal to, if z is just equal to I, okay, let's find the 8th roots okay? So we're going to find z to the 1/8, and we're going to find all 8 of those roots, okay? So here's the thing. This is very arbitrary. I guess not arbitrary. What's the word I'm looking for? It's so simplistic that it confuses people. Last class we did this one. We said z equals 1, and it's confusing because it's not as obvious that that's an a plus bi. Does that make sense? And that it's in rectangular form. This is not as obvious. It's a little bit more obvious because of the I, but it's not real insightful that it's a plus bi. That is in rectangular form. So to use this property, we have to change it to polar, right? Okay. So let's change this thing to polar form. So z in polar form, remember, it's a squared. So this thing 0i is the same thing as 0 plus I, isn't it? Okay. So a would be 0, and b would be 1, right? So what do I get for my radius? Just 1. Okay. Theta, you can use tangent inverse of b over a, but it gives you this, and your calculator is going to say that that thing is undefined, right? And this is a situation where you most definitely need a picture. If I go 0 plus I, that means move 0 on the real axis, and then up 1 on the imaginary axis, right? What would that theta be right there? Pi over 2, okay? So what I'm looking for, z equaling I in rectangular form is z equals 1 cis pi over 2 in polar. Is that doable? So now if I'm going to find the 8th roots of these, okay, so z to the 1/8 would be 1 cis pi over 2 to the 1/8, which now you take the 8th root of 1, and you go cis, and then you take your theta plus 2 pi k over n, but n is what in this case? 8. And now here's the problem, is that we got to go k is equal to 0, k is 1, k is 2, k is 3, k is 4, k is 5, k is 6, and k is 7, right? We go up to n minus 1 because that's going to provide me, then if I started at 0, it provides me 8 roots. Now in all of these, what's 1 raised to the 1/8? What's the 8th root of 1? It's just 1, right? Okay, so all of these are going to have a radius of 1. So they're all on what it turns out to be the unit circle. They're all going to have a cis. Okay. Now, if k was 0, that goes away. And you're left with pi over 2 divided by 8, right? So that becomes pi over 16. Okay. If k were 1, I'd have pi over 2 plus 2 pi k, okay, which with a denominator would be 4 pi over 2, right? So that's 5 pi over 2 all over 8, which would be 5 pi over 16. Do we now have our common difference? It's 4, right, in the numerators? So is this one going to be 9 pi over 16? This one's going to be 13 pi over 16, 17 pi over 16, 21 pi over 16, 25 pi over 16, and 29 pi over 16. You should be able to kind of generate those that fast. Does that make sense? I do not want to have to evaluate pi over 2 plus 2 pi k over 8 for every one of those 8k values. Okay, find the common difference and go that route. So let's see, and we can always check ourselves. Now it's a pain in the butt because we got 8 of these things to look at, but we can check ourselves, and hopefully you use like a cut and paste process here to do this. But 0 plus I, obviously that's z sub 1. So then if I go, I'll just say w sub 1. Let's go w sub 0 is equal to 1. Now cosine of pi over 16 plus I times sine of pi over 16 should give me that point there. Okay. Okay, so the blue point is that. So I'm going to go Control C, Control V, put this as 1, and now I need a 5 there and a 5 there. Hit enter. Do the same thing, but now I need this to be 2, and I'm going to put a 9 here. 9 and 9. And then I need 3. And what I'm going to put, so 3 was 13. Oh. There, and 13 there. What was the next one? 4 was a 17. Uh, 5 was it 21? Is that right? 21? 6, 25. And 7. All right, now I'm going to zoom in on this thing. Are those all on the same circle? Okay, so that kind of tells me that I'm doing things correctly here. And even this is a special one. Even the complex number that I started with, z sub 1, that is even on that circle, right? That's because it had a radius of 1, and square root of 1 is 1, right? 8th root of 1 is 1. So that's why that stays on the circle. But if I take any one of those w's, and I say w sub 6, and I raise that to the 8th power, it puts me back right on top of that point right there. Okay, so I do have those roots. We can look at the angle that's between any two of these, or any two consecutive ones, and we get 45, because 360 divided by 8 is 45. Okay. So those are kind of the relationships that we see. A lot of symmetry there, right? Okay. With those 8 roots. That is kind of the conclusion of the Moyer's theorem, okay, and being able to use it to raise something to some power, whether that power be an integer, or in this case, that power be 1 divided by some integer, okay, so an nth root. That's going to wrap up Chapter 8, guys. We don't get into the next section, which is plane curves and parametric equations. So tomorrow, my plan is to start looking at kind of an intro to vectors. Talk about vectors tomorrow and 3 or 4 days next week. Then Friday of next week have a chapter 8 and 9 test, somewhat similar to the length of the last test we took over chapter 7. Then we'll do a review for 2 days and have our exam. We'll start the exam on Wednesday, Thursday, and then the Friday. I think Friday's your last day, seniors, right? If we need that buffered time, we can have. So it's not next Friday, the following Friday. We'll have that extra time if we need it.